Picture this. You're sitting in the left seat of a Cessna.
Oh, the best seat in the house.
Right. You are a high school student, and you've spent weeks, poring over aerodynamics, charting out cross-country routes, and just dreaming of this exact moment.
You've put in the work.
Exactly. Your hands are on the yoke. You know the mechanics of flight. You are airborne. But then suddenly, a voice crackles over the headset.
But it is fast.
Yeah, rapid fire, just filled with letters and numbers that sound like some kind of secret code, and whoever is talking is waiting for your response. Do you know how to answer?
You know, that transition going from just understanding the physical aerodynamics of an airplane to actually navigating the shared airspace system that is usually the steepest learning curve for a student pilot.
I can imagine.
Yeah, because you stop operating in isolation, right?
Yeah.
Suddenly you have to integrate into this massive, invisible, super fast-moving network.
And that is our mission today. For this deep dive, we are officially adopting the roles of your certified flight instructors.
Welcome to ground school.
Glad to have you. Our goal today is to teach you the language of the skies, basically how pilots communicate with air traffic control and with each other.
And we've got a great stack of flight manuals we're pulling from today.
Yeah, the definitive sources. We're looking at the Airplane Flying Handbook, the Pilot's Handbook of Aeronautical Knowledge, and the Aeronautical Information Manual.
Which, those manuals really represent the foundational architecture of the whole national airspace system. They outline the precise protocols that keep, thousands of metal objects from colliding at hundreds of miles an hour.
Okay, let's unpack this. Before we teach you the actual vocabulary of the radio, we really have to look at the psychology of when to actually use it.
Yeah. Spoiler alert for our aspiring pilot listening.
Yeah.
Picking up that microphone is absolutely not your first priority.
Not even close.
The manuals are super uncompromising on this point. They prioritize a really strict foundational hierarchy, which is aviate, navigate, communicate.
Often just referred to as A and C.
Right, A and C. You're already studying aerodynamics, so you know what it takes to physically aviate. You know how to navigate a route. Communication comes dead last.
Because if you reverse that order, well, human history is full of tragic case studies showing why that's fatal.
It really is.
The 1972 crash of Eastern Airlines Flight 401 is the textbook example of this. You had this massive Lockheed L-1011 flying into Miami at night, right? And the crew noticed a landing gear indicator light wouldn't turn on.
Just a tiny $10 light bulb on the instrument panel.
Literally. But rather than maintaining their prioritization, the entire flight crew just succumbed to cognitive tunneling.
Yeah, they focus completely on troubleshooting and communicating about this one minor malfunction.
And because their collective attention was totally consumed by that single task, the primary act of aviating was dropped. The autopilot got inadvertently bumped and disconnected.
And that massive aircraft just slowly descended right into the Everglades. No one even noticed the altitude dropping because their mental bandwidth was totally maxed out.
For our high school listener, it's exactly like texting while driving.
Oh, that's a perfect analogy.
Right. It doesn't matter how important the text to your mom is or how perfectly punctuated it is. If you drive into a ditch while typing it, you have to drive the car first. You have to fly the plane first.
What's fascinating here is the underlying neurology. The flight manuals actually discuss this under the umbrella of task management and cognitive overload.
Which is a very real physical limitation, right?
Absolutely. The human brain has a hard physical limit on how much sensory input it can process simultaneously. Think about your vision. Your foveal vision, that tiny central area of sharpest focus, is only a few degrees wide.
So you physically cannot look at two distinct instruments at the exact same time.
Exactly. And hearing and auditory processing work the exact same way. You cannot actively process two complex verbal streams at once. So when a pilot reaches cognitive saturation, new information literally just bounces off.
They fixate on one thing and the critical tasks just fall away.
Yeah. So to counter this, the manuals teach the 3P model. Perceive, process, perform.
It's kind of a continuous loop, isn't it?
Right. A continuous mechanical loop of situational awareness. So you perceive the environment like recognizing you're spending too much time trying to figure out a garbled radio transmission.
Okay, and then you process the implication.
Yeah, realizing, uh-oh, my airspeed has dropped dangerously low while I was distracted.
And finally, perform.
You perform the action. You abandon the radio, push the yoke forward, and recover your airspeed.
Yeah.
Pilots use this loop to actively triage their attention so they never end up, as we say in aviation, behind the aircraft.
Love that phrase. Okay, so let's assume you've mastered the 3P model. The aircraft is straight and level. You are aviating flawlessly, and you are navigating accurately, say, 10 miles south of your destination.
Beautiful. Now you actually have the mental bandwidth to communicate.
But the very first rule of the radio requires absolute silence. You have to listen before you transmit.
Because aviation radios operate on VHF, or very high frequency analog bands. It's a totally shared open frequency.
So what happens if two people hit the talk button at the exact same time?
Well, the analog waves overlap and actually cancel each other out. It's a phenomenon called a heterodyne.
That sounds intense.
Yeah, anyone listening just hears this awful, high-pitched, squealing tone. Nobody's message gets through. So by pausing and just listening for a few seconds before keying the microphone, you ensure you aren't stepping on someone else's critical clearance.
Makes total sense. Now, when you do verify the frequency is clear and you key the mic, you are entering a world governed by the ICAO phonetic alphabet. Alpha, Bravo, Charlie, Delta, all the way to Zulu.
The universal language of aviation.
But I have to push back on this a little bit.
Oh.
Yeah, like, if I am flying a Cessna with the tail number N123B, isn't it just faster to say N123B? Insisting on November 123 Bravo feels like, I don't know, performative military overkill when I'm just trying to check in with my local tower.
I get why it feels that way. But the phonetic alphabet is actually an engineering necessity. It's completely driven by the physics of VHF radio waves and, really, the acoustic properties of the English language.
Wait, really? The physics of the radio waves?
Yeah, VHF relies on line-of-sight propagation. The signal doesn't bend around the Earth, and it is highly susceptible to atmospheric static, alternator whine, engine noise.
All the loud stuff in a tiny airplane.
Exactly. So if you just transmit the letter B through a thick layer of static, the human ear physically cannot distinguish it from C, D, E, G, P, T, V, or Z.
Oh, wow. Because they all share that same harsh consonant-to-vowel structure. They all rhyme.
Right. The acoustic signatures are nearly identical over a scratchy, low-fidelity cockpit speaker. Imagine a controller issues a landing clearance to aircraft 123B.
But aircraft 123C is on the same frequency.
And 123C perceives that clearance as theirs. You've instantly created a massive mid-air collision risk. But words like Bravo and Charlie, they have completely distinct syllable structures and vowel sounds.
So even if static cuts out half the word,
The remaining acoustic footprint is still identifiable as Bravo. This absolute need for acoustic clarity is exactly why CB radio slang, or just conversational filler, is strictly prohibited. It's a highly engineered, functional language.
clarity over everything. I like that. And before we even dial up the tower to land, the manuals require us to gather local data using the ADIS, right? The Automatic Terminal Information Service.
Yes, the AD is an ingenious system. It's designed specifically to reduce radio congestion.
Because busy airports would be a nightmare otherwise.
Exactly. At busy airports, a totally separate radio frequency constantly broadcasts a recorded loop. It details the local weather, wind direction, active runways, and any temporary hazards, like closed taxiways.
And to verify that pilots have actually listened to the most current loop, each hourly update is assigned a sequential phonetic letter.
Right. So you tune in, you listen to the loop, and the recording concludes with something like, advise on initial contact, you have information, Sierra.
And then when you subsequently call the tower, you just append your call with, I have information, Sierra.
Yeah, because that single phonetic letter is basically a data compression tool. You're telling the controller, I already possess the current altimeter setting, wind vectors, and runway configurations. You do not need to waste valuable airtime transmitting them to me.
But I've noticed some pilots try to shortcut this by telling the tower, I have the numbers.
Oh, yeah.
But the Aeronautical Information Manual explicitly warns against confusing those two phrases, doesn't it?
It does, and the distinction is hypercritical for safety.
Why is it so different?
Because stating you have numbers strictly implies you only obtain the wind, runway, and altimeter setting. Maybe you got it from a digital data link or heard a previous transmission.
Oh.
It signals to the controller that you have not listened to the full ATIS loop, which means you might be completely ignorant of a closed runway, an unlit tower, or an equipment outage that was mentioned in the broadcast.
So have numbers is never an acceptable substitute for actually having the current ATIS information. Good to know. Okay, so with Information Sierra securely in mind, it's time to structure the initial radio call. Aviation communication relies on a really strict four-part anatomical structure, right?
It does.
Who you are calling, who you are, where you are, and what you want.
That structure just eliminates all the conversational padding. You don't say hello, you don't ask how they are, you simply state Springfield Tower, Cessna 123 Alpha Bravo, 10 miles south, inbound to land with information Sierra.
Let's break that down. Who you were calling. Springfield Tower, who you are. Cessna 123 Alpha Bravo, where you are, 10 miles south. And what you want. Inbound to land with information Sierra.
Perfect. Every pilot and controller expects that precise cadence, because when the sequence is predictable, the human brain processes the information much faster and with way fewer errors.
Here's where it gets really interesting. We've mastered the syntax, so let's put our high school pilot into the actual airspace.
Let's do it.
We know how to talk to a controller, but what happens when there is no controller? I mean, thousands of small airports operate entirely without control towers.
Yeah, it's basically the Wild West of aviation.
It really is.
Operating at a non-towered airport shifts the entire burden of separation away from an ATC facility right directly onto the pilots flying in that vicinity. It really functions as a highly structured honor system.
And pilots self-coordinate their movements using a shared frequency called the CTAF, right? The Common Traffic Advisory Frequency.
Exactly. The FAA has carved out specific bandwidths just for this purpose.
Right. You'll frequently see Unicom frequencies on like 122.7 or 122.8 megahertz.
Yeah, and a Unicom might have an airport manager sitting at a desk inside who can give you a quick wind check, but they have zero authority to actually control traffic.
And if an airport doesn't even have a Unicom?
Then you use the multicom frequency, which is uniformly 122.9 all across the country. And these 122 megahertz frequencies are intentionally totally segregated from the bands used by air traffic control.
So the advisory chatter never bleeds into controlled airspace operations.
Precisely. So as you approach a non-towered field, the protocol requires you to begin broadcasting your position and your intentions on the CTAF starting about 10 miles out.
But the structure of a CTAF self-announcement differs a little bit from a tower call, doesn't it? You have to, like, sandwich your transmission with the name of the airport?
Yeah, the sandwich technique.
So you'd say something like, Midwest traffic, Cessna 123 Alpha Bravo is 10 miles south, inbound for landing, Midwest traffic.
Exactly. And that sandwiching technique solves a real problem with finite radio bandwidth. The CTAF you're utilizing is almost certainly being shared by several other small airports within, say, a 100-mile radius.
Oh, right, because of the VHF line of sight you mentioned earlier.
Right, so a pilot 50 miles away might be tuning the radio and only catch the tail end of your transmission. If they just hear pointed 10 miles south, inbound for landing, they might assume you are converging on their airport.
Which would be terrifying.
Yeah. So concluding with the name Midwest Traffic provides immediate geographic context to anyone who missed the very beginning of the call.
Now, there is a specific phrase you'll occasionally hear on the CTAF that I know makes flight instructors just grind their teeth.
Oh, I know exactly what you're going to say.
The FAA has explicitly stated in the manuals that it shouldn't be used. That phrase is, any traffic in the area, please advise.
Ugh, yes. It is a legacy phrase from decades past. It clogs the frequency and provides zero actionable data.
To give our high school listener an analogy here, using the phrase, any traffic, please advise, is like walking into a pitch black room in your house and yelling, is anyone in here?
Instead of just turning on the light and announcing I'm walking to the fridge.
Exactly.
The analogy holds up really well. If you state exactly who you are, where you are, and what your trajectory is walking to the fridge, any other entity in that airspace can immediately calculate if your paths are going to intersect.
Right, and if a conflict does exist, they will naturally transmit their own position to resolve it.
Exactly. Prompting them to speak simply wastes bandwidth and, frankly, it assumes other pilots aren't already monitoring the frequency.
Makes sense. So once you actually enter the physical traffic pattern around the runway, the self-organization just continues. Unless a chart explicitly notes an exception, like maybe due to terrain or noise abatement, all turns around a runway are standard left-hand turns.
If we connect this to the bigger picture, the entire non-towered ecosystem is anchored by the legal and practical concept of see and avoid.
See and avoid.
Yes. The pilot synthesizes auditory data from the radio with visual data outside the cockpit to build a mental map of the surrounding airspace.
So why the left turns specifically?
Standardizing left-hand turns gives a huge physiological advantage. Since the pilot in command traditionally sits in the left seat of the aircraft, making left turns keeps the runway and the surrounding traffic clearly visible out the pilot's side window throughout the entire maneuver.
Oh, that's brilliant. It's just an incredible system of distributed awareness. But let's leave the non-towered environment behind for a second and fly into complex, controlled airspace. like Class B, C, or D airspace surrounding major cities and large airports.
The paradigm shifts completely here.
Yeah.
The honor system is totally replaced by active positive control.
So to legally cross that invisible boundary into Class B, C, or D airspace, just self-announcing on the radio is insufficient.
Totally insufficient. You are legally required to establish two-way radio communication with the controlling facility.
And the legal definition of establishing two-way communication is surprisingly strict. It requires the controller to respond using your specific aircraft call sign.
Yes.
Like, if you broadcast Springfield Tower, Cessna 123 Alpha Bravo, and the tower replies, aircraft calling Springfield, standby. Have you established communication?
No, you absolutely have not. You must remain outside the airspace. The controller has to validate your presence by name.
Once they do, and you're inside, the communication becomes highly prescriptive. Air traffic control issues binding clearances and instructions, and pilots are required to read back specific directives.
And the most critical of these are hold short instructions.
Right. A controller might clear you to taxi to runway 27, but instruct you to hold short of runway 31 along the way. You can't just reply Roger to that, can you?
Definitely not. You must verbally repeat back, holding short runway 31, Cessna Alpha Bravo.
Why isn't Roger enough?
Because Roger simply means I have received your transmission. It does not mean I understand and will comply. Verbally reading back the hold short instruction is a forced error checking mechanism. It literally proves to the controller that the pilot understands exactly where they must stop their aircraft to avoid, say, taxiing right into the path of a departing Boeing 737.
That is crucial. Now, communication in controlled airspace isn't just limited to voice. The airplane itself is actually talking to the ground via the transponder, right? Interacting with the secondary surveillance radar system.
Yeah. Primary radar works just by bouncing raw radio waves off the metal skin of an aircraft to detect its position.
Pretty old school.
Very. But secondary surveillance radar, or SSR, is much more advanced. The ground station sends out a 1030 megahertz interrogation pulse. Your aircraft's transponder receives that pulse and instantly broadcasts a digital data packet back on 1090 megahertz.
And this is where squawking comes in. Air traffic control will instruct you to squawk a 4-digit octal code, for instance, 4215.
Right. And when you input that into the transponder, it includes that specific code in its data packet.
So the ATC computer matches 4215 to your flight plan.
Exactly. And suddenly that anonymous blip on the controller's screen transforms into a detailed data block showing your exact call sign, altitude, and speed.
And sometimes controllers will ask a pilot to squawk 4215 and ident. Now, ident stands for identify, and it's an actual physical button on the transponder faceplate. But what mechanism is actually triggered when you press that ident button?
So pressing ident alters the data packet your transponder transmits for about 20 seconds. It adds a special pulse bit.
Okay, when the ground computer receives this altered packet, it forces your specific data block to flash or bloom intensely on the controller's radar scope.
Oh, so if a controller is managing 50 aircraft in a crowded sector, asking you to ident instantly highlights exactly which target is yours.
Precisely. It cuts through the clutter.
Now, air traffic control manages vast amounts of airspace, but it's broken up into geographical sectors. So as you fly cross-country, you don't just stay with the same controller the whole time.
No, the system utilizes constant handoffs. As you approach the boundary of one sector, the current controller coordinates with the next sector's controller.
And they instruct you to change frequencies, like Cessna Alpha Bravo, contact center on 124.5.
And you read back the new frequency, tune your radio, and establish contact with the new controller, ensuring totally seamless radar coverage across the country. So, what does this all mean for our student pilot navigating this heavily managed environment? Like, if an air traffic controller is orchestrating this massive system, issues me a vector, and that vector points me directly into a towering thunderstorm cell or a mountain ridge, do I just blindly follow the instruction because ATC is in charge?
Under no circumstances.
Really?
This touches on the absolute bedrock of aviation safety. The ultimate authority and responsibility for the safe operation of an aircraft rests with exactly one individual, the pilot in command.
That's the pilot sitting in the left seat.
Exactly.
Yeah.
ATC provides phenomenal situational awareness, sequencing, and separation. They're a vital component of crew resource management.
What?
But they're looking at a two-dimensional radar screen. You're looking out the window. If a clearance jeopardizes the safety of your flight, you have the legal right and the moral obligation to refuse it.
You can just say no.
You simply transmit, unalertable. You can request an amended clearance, or if necessary, declare an emergency and deviate from literally any rule to meet that emergency. Remember the golden rule. Aviate first. ATC cannot fly the airplane for you.
That is incredibly empowering for a student pilot to hear. But, the entire system we just outlined, the clearances, the handoffs, the radar identification, it all relies on a single glaring point of failure.
The radio hardware itself.
Exactly. A single broken wire behind the instrument panel or a failed alternator, and suddenly you are completely cut off.
A total communications failure is known as a NORDO situation, signifying no radio. It really strips away the primary layer of safety in controlled airspace.
Let's play this out. Let's say I'm Nordo. I'm flying toward a busy towered airport. The hardware is dead. How do I physically get on the ground without triggering a mid-air collision or causing a massive ground incident?
The manuals prescribe a highly visual set of backup procedures for this. First, you remain outside the controlled airspace and just observe.
Look for the traffic.
Right. You determine the active runway by watching the flow of departing and arriving traffic. Once you safely sequence yourself into the traffic pattern, you look directly at the control tower cab. The controllers, recognizing a Nordo aircraft on their radar, will utilize a directed light gun to communicate with you.
So it's essentially a high-intensity focused spotlight projecting specific colors at your plane.
Exactly. A steady green light directed at your aircraft means you are cleared to land. A flashing red light means the airport is unsafe and you must circle or divert.
But since I lack a functioning transmitter, how do I say Roger? I have to acknowledge the light signals mechanically, right?
Yes. During the day, you physically rock the airplane's wings. At night, you flash the landing lights to signal compliance.
Okay, light guns solve the local landing issue, but you also need to alert the broader air traffic system that you have a problem before you even get there.
Which is where your transponder becomes an emergency beacon. There are 3 dedicated emergency squawk codes.
Right, squawking 7500 indicates a hijacking, and squawking 7600 alerts ATC to a lost communications situation.
And that 7600 immediately triggers visual alarms on the controller scopes, alerting them that you cannot hear their instructions.
What about the third code?
If the situation is a severe, life-threatening emergency, like an engine failure, or an onboard fire, you squawk 7700. The 7700 code alerts the entire ATC facility, automatically highlighting your aircraft so they can instantly clear the surrounding airspace and prepare emergency ground services.
Now, if the radio is functioning during a severe emergency, pilots utilize universal vocal distress signals. The most severe is, of course, Mayday.
Yeah, derived from the French Mater, meaning help me. A Mayday broadcast indicates grave and imminent danger requiring immediate assistance.
And there's a protocol for using it, right?
When a pilot transmits Mayday, 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 it legally commands absolute radio silence on that frequency. All other pilots must cease transmitting immediately. The frequency belongs exclusively to the distressed aircraft and ATC.
There is a secondary tier of distress call as well, the pan-pan.
Right. Pan designates an urgency situation. You have a critical issue, perhaps an alternator failure, a passenger experiencing a heart attack, maybe an orientation problem, but the aircraft is not currently falling out of the sky.
So it's serious, but not quite a Mayday.
Exactly. A pan call takes priority over all standard communications, yielding only to a Mayday.
Okay, the Nordo scenario in clear weather makes total sense to me. You squawk 7600, you watch the tower for the green light. But what happens if you lose your radio while flying under instrument flight rules? IFR.
Oh, the nightmare scenario.
Right. You are embedded in a thick cloud layer. You cannot see the ground, you cannot see other traffic, and you certainly cannot see a light gun from the tower. Do you just wander through the clouds hoping you don't hit an airliner?
Thankfully, no. The IFR lost communications protocol is actually one of the most elegant pieces of logic in the aviation manuals.
Really? How so?
It relies on absolute predictability.
Oh.
If you go Nordo in the clouds, you are required to fly your route based on a strict hierarchy known by the acronym AVEF.
Okay, AVEF.
Yes, assigned, vectored, expected, or filed.
So you fly the route you were last assigned by ATC.
Right.
If you were being radar vectored, you fly direct to the fix you were being vectored to. If neither applies, you fly what they told you to expect in your clearance. And as a absolute last resort, you fly the route you originally filed in your flight plan.
You've got it. The brilliance of the AVEF algorithm is that the controllers on the ground know you are following it. Because you squawked 7600, they know your radio is dead.
Ah, so because the rule is standardized.
The controller can predict your exact heading, your precise altitude changes, and your arrival time at the destination. They simply clear every other aircraft out of that specific geographic tunnel, allowing the silent blind aircraft to navigate safely to the runway.
That is amazing. Standardized procedures turn an inherently chaotic crisis into a highly structured, manageable event.
It really is a beautiful system.
It is a remarkable safety net built entirely out of procedural agreements. Well, we have covered a massive amount of airspace today. Let's bring it in for a landing.
Sounds good.
For the high school student preparing to take the left seat, here is your final exam summary for Communications Ground School. Number 1, always respect the cognitive limits of your brain. Aviate first.
Fly the plane.
Number 2, master the phonetic alphabet and VHF protocols to guarantee clarity. Number 3, understand your environment. Know how to self-coordinate on a CTAF and how to integrate into the radar environment of controlled airspace.
Crucial.
And finally, number 4, always understand the mechanical backup plans for when the hardware fails.
I'd say you've passed ground school. You're officially equipped to speak the language of the skies.
We are officially signing off as your flight instructors, but before we close the hangar doors, we always leave you with one final thought to explore.
And this raises an important question regarding the evolution of technology.
Hmm.
I mean, the analog VHF radio has been the backbone of aviation for decades, but the modern cockpit is rapidly transitioning to digital data link communications.
Right, like systems like ADS-B that automatically broadcast GPS positions without any pilot input.
Exactly. And commercial pilots are increasingly receiving complex ATC clearances digitally, just via text directly onto their cockpit screens, which eliminates acoustic misunderstandings entirely.
Oh, wow.
So as these data link architectures become universally adopted, will the human voice on the radio eventually become entirely obsolete? Will the pilots of the future evolve into silent system managers, orchestrating complex flights without ever speaking a single word to the ground?
A completely silent airspace system. That is a fascinating paradigm shift to consider the next time you watch a jet paint a contrail across the sky. Until next time, keep studying, and remember, always fly the plane first.